Hello, everybody, and welcome back with another school year. I don't know about you, but I am super excited that we are diving in again with another year of science, exploration, and conservation here at Exploring by the Seat of Your Pants. For those who are joining us for the first time, my name is Jesse. I am your virtual adventure guide to our over 500 planned programs this year. Pretty much every year, we do 500 plus programs with amazing scientists, conservationists, explorers around the planet, and I'm so thrilled you are all joining us today as we kick off another epic school year with one of the coolest topics I can possibly imagine. Now, before we dive in, I'll just say a quick hello to all our YouTube classes as well. If you want to let us know where you're joining from in that chat bar, I'd love to see where you're all coming from today. We've got groups registered from Ghana in West Africa, I think about 7 US states, 5 Canadian provinces all over the world, so welcome into all of you. We are going to be having a Kahoot today, so if you're unfamiliar with Kahoot, we'll walk you through it a little bit more later in the broadcast, but you can open up a separate tab on your computer now and type in this game pin to get ready for a little 4-question interactive quiz between our talk and our Q&A portions. Again, if you haven't checked us out before, exploringbytheseat.com has absolutely everything. We've already got about 30 broadcasts planned in September. Now today, I'm so thrilled to kick off our school year with one of my very favorite speakers, Dr. Nathalie Ouellette. So she is an exoplanet scientist. She's an astrophysicist. She's at the Institute for Research on Exoplanets at U Montreal. And notably for today, she is the lead Canadian outreach scientist for the James Webb Space Telescope. So many of your classes and families will have seen this incredible telescope has gone out to space and started sending back these amazing images of the universe heretofore unseen. And so today, with Nathalie, we are going to walk through a little bit about what the telescope is discovering and blow a few of your minds. And so without further ado, I'm going to bring in Dr. Nathalie Ouellette. Thank you so much for joining us today. And take us away. Hi, what's this telescope all about? What's it seeing? I can't wait to learn more myself. Never mind the kids. I'm sure we're all comfortable.
Yeah, I'm so excited to kick off the new school year. I remember always being very excited about starting school again when I was a kid. I loved learning, and I'm so fortunate that I get to continue learning and also teaching now. So we're going to have such a great time today talking about the James Webb Space Telescope, everything it's been doing, and what it's going to be doing in the future as well. But before we jump into the telescope itself, we need to sort of think about how we look at the universe. So astronomy's been around for a very, very long time. And one of the great things I love about astronomy is everyone can do it. You don't even need a tool. You don't need a telescope. You can just go outside, look at the night sky, the moon, the planets, and observe the things yourself. But over time, over hundreds of years, we've started developing different instruments. And one of the reasons we've developed different instruments and different types of telescopes is because there are different kinds of lights that exist. So you might know the visible light that we can see with our human eyes. Those are the colors of the rainbow. And the sun is very bright in that kind of light. So we've used this to navigate the world, but there's all different kinds of light, going from very long radio waves that we use to communicate with each other over long distances, going through infrared light, which you might have seen in like sci-fi movies. It's very connected to heat, visible light, of course, and also ultraviolet light that we need to protect ourselves from with sunscreen, X-rays, and gamma rays. And these are all different kinds of light that the universe shines in depending on the different objects that you're looking at. So we want to study all these different objects using these different kinds of light. So we need special eyes to do that, and that's what telescopes are. But we live on the Earth, in the atmosphere of the Earth, that blocks out some of these different kinds of light. So what is the best place to put a telescope? You might have gone in the countryside, going camping, going to a cottage, and you might have noticed that it's a lot nicer to look at the night sky there because there's no light pollution. And it's true, going out there where it's really dark, it's better to put a telescope there. But if you want to do even better than that, the best place to put a telescope is out in space, because there's absolutely no light pollution, there's no clouds, and you're above the atmosphere of the Earth. So you can look at all the different kinds of light like, for example, infrared light or X rays that are typically blocked out by the atmosphere of the Earth. But there are disadvantages. It is harder to put something out into space than it is to build something out on the ground, even if it's far away from a city. And if it breaks, it's harder to fix or even impossible to fix. So it's important to have telescopes both on the Earth, on the ground, and in space. And you can't talk about a space telescope without talking about the Hubble Space Telescope, a really, really breakthrough telescope that was launched in 1990. So it's getting kind of old. It just celebrated its 32nd anniversary, its birthday this year, but it's been doing incredible science since those 32 years of operations. And it's been taking incredible images as well. So I actually grew up in Montreal. I had a lot of light pollution. I didn't have a nice night sky, but I grew up with the images from the Hubble Space Telescope and I fell in love with astronomy through this mission. So a really wonderful mission. You can see it's actually orbiting very close to the Earth, about 520 kilometers above our heads, but it is getting older. So for a long time now, we've been planning the successor, sort of like what's going to take over that part of astronomy from the Hubble Space Telescope, and that is the James Webb Space Telescope. So this started planning in the mid 1990s, and we started building it over time. And finally, we've been able to launch it and start its operations very recently. So this is a mission that's led by NASA. About 10,000 people have worked on this mission. It's a huge, huge mission, and it had two partners. Was working with two partners, the European Space Agency, who were involved in the Hubble Space Telescope. Very exciting for me and for everyone out there who's in Canada, the Canadian Space Agency was involved with the Webb Telescope. And we weren't involved in Hubble. So this is really, really a big deal for us. And I'll tell you a little bit about the contribution that Canada made to this mission. So, of course, this is a telescope. Its focus is astronomy and learning what's going on in space. So, a scientific instrument, but it's also an incredible technological wonder. And I, as the outreach scientist for the Webb Telescope, get to be the bridge between the science team and the general public to talk about all the wonderful things this technological marvel is able to do. It's really, really wonderful. This is a picture of me visiting the telescope a few years ago before it was launched into space, of course. It's a good picture that shows how much I love the mission, how involved I am. But I think an even better picture to show how much I love this telescope is this picture right here. This is a picture of my Halloween costume last year. I dressed up as the James Webb Space Telescope, and I gave out candy, and people loved it. So I love doing outreach in sort of like unique, different ways, and have a great conversation starter, like a big, giant space telescope costume. So I mentioned this is a scientific tool, but a really, really huge achievement in terms of technological wonder. It's a huge telescope, the biggest space telescope we've ever launched. The mirror, which is the main part, is 6.5 meters wide, so a really, really big mirror. It's composed of 18 little hexagon pieces, and you might have noticed it looks sort of like a honeycomb. It's coated in gold, and the big piece underneath is as big as a tennis court. So it's so big, in fact, that in order to get it to fit into the rocket that launched it, we needed to fold it on itself. So as soon as we started developing this telescope, we made it so it was foldable, like a piece of origami. But if we fold it up, that means that we need to unfold it when it's launched into space. So we launched this finally after decades of work last Christmas, so December 25th in the morning. It was launched from Kourou in South America on an Ariane 5 rocket. And it was a really emotional moment for everyone in the mission. Um, when it was launched up, all the pieces of the rocket came off, and you can see this is a video of what the deployment or the unfolding of the telescope looked like. And it wasn't doing this while it was parked next to the Earth. We actually are launching this telescope, and we have launched it 1.5 million kilometers, or about 1 million miles away from the Earth. That's 4 times farther away than the moon is. And we've never sent a human out that far. That means if something goes wrong with the telescope, we cannot fix it, which is why we took so much time developing and testing it before we launched it into space. So here you can see that the big piece underneath the telescope is unfurling now. This is what we call the sun shield, because this is one of those telescopes that looks at invisible light to humans. It looks at infrared light, very associated to heat. So we need to protect the telescope, the mirror, and the instruments on the telescope from the heat of the sun. Because if the sun heats up the telescope starts glowing in the infrared itself, which is bad. It's causing its own light pollution if it does that. So the sun shield, as big as a tennis court, very, very important piece. 5 layers of this very reflective material. And then you have the mirror right now that you can see unfolding, all those little 18 honeycomb segments, and it's coated in gold because gold is the most reflective material to use to reflect infrared light. And we're so excited now. It's 1.5 million kilometers from the Earth, and it's doing its thing. It's working really, really well. So it was a huge adventure getting it out there, but it worked really well. So this is Canada's contribution to the mission. So you saw the big mirror, and behind the mirror, there's a box with 4 instruments inside of it. And we gave one instrument, but it's a 2-for-1 deal. So on the top part of the instrument, you have what we call the fine guidance sensor, or if you want, you can call it the Canadi. So you maybe have heard of the Canadarm. We have an arm, a robotic arm on the International Space Station, but we have an eye on the James Webb Space Telescope, which allows the telescope to lock on to the specific target it wants to look at and make sure that that target stays right in the center of its field of view. So very, very important. It's not a scientific tool, but it's used for every single observation taken by the telescope. And under the instrument is the other piece. It's called the NIRS, or the near infrared imager and slitless spectrograph. It's a combination of a camera that can take pictures, but also a spectrograph, which can take spectra. So a spectrum is when you take the light of a faraway object and you break that light into the composing colors, sort of like when you take a light, you put it through a prism and you create all the colors of the rainbow. You do that for infrared light as well. And that gives you more information about things like the temperature, the distance, the movement, the age of different objects. So you get lots of information from that. So this is our little contribution, the Canadian instrument. It's at the back of the mirror. It's about the size of a washing machine. And the Canadian Space Agency was the lead on all this, but we had people from the University of Montreal working on it, from NRC in Victoria. Honeywell was our main industrial partners, and tons more people in Canada working on this over many, many years to give the Canadian contribution to the mission. So, what is Webb observing exactly? So, it has 4 main missions that it wants to look at. The first one is called Alien Worlds, and that is worlds that are not the Earth. They can be in the solar system or they can be beyond the solar system. So, worlds or planets that orbit stars other than our sun, those are called exoplanets, a very important mission for Webb. It's also interested in the life cycle of stars. So, stars, all the way from them being born to when they die, and when they die in a spectacular death, turn into a supernova and maybe even turn into a black hole. So it wants to study how stars evolve over time. But it is also interested in galaxies and how those galaxies evolve over time as well, from the very beginning of the universe all the way to what they look like now and the galaxies that are close to our own galaxy, the Milky Way. It also wants to look farther back into the universe than any other telescope has ever looked at. Because you might know, astronomy is a very special science. And because of that, we can actually use telescopes as time machines because light takes some amount of time to travel the very, very far distances in space. When we look at the light of a distant object, it's actually old light. So if you look at something that's 10 billion light years away, we're not seeing that object as it is now. We're seeing it as it was 10 billion years ago. So we want to use the Webb telescope to look as close to the Big Bang at the very start of the universe as possible. So now we're going to look through some of the first images of the Webb telescope together to get you really excited about what's coming up next. So the first mission I mentioned is observing alien worlds, so exoplanets. So these are very distant worlds, and you can see here this is an artistic representation because we can't take a picture like this yet of those kinds of planets. They're too far. They're not like the ones in our solar system where we can just send a probe and take a picture there. So the way that we detect or spot an exoplanet is by looking at stars. And if an exoplanet passes in front of a star, it sort of causes like an eclipse. The star becomes a little bit less bright. And if the planet is bigger, it causes a bigger eclipse. So it becomes even less bright. So by doing this, we can actually detect an exoplanet and get lots of information like its size, maybe its composition, how close it is to its star, which gives its temperature. So lots of interesting information. And when the planet passes in front of its star, if the planet has an atmosphere, the light of the star actually passes through that atmosphere and is imprinted by interesting molecules and all different kinds of things inside that atmosphere. So that gives us a spectrum, which is something that looks like this, a line with a bunch of wiggles and bumps. But we, as astronomers, can read all those different wiggles and bumps, and the wiggles and bumps are actually sort of like a fingerprint of the atmosphere of the exoplanet. And in this case, using the Canadian instrument on the telescope, we looked at a hot, big Jupiter like planet called WASP 96b, and we detected water vapor in the atmosphere of this exoplanet. Even though it is over 1,000 light years away, so far away, we can tell there is water vapor in the atmosphere of this planet. So, so exciting, especially as we're trying to find alien life eventually. And we know water is super important for life in the universe and on Earth as well. This is another picture here, and this is about the life cycle of stars that I mentioned. So this is called the Carina Nebula, and we've nicknamed it the Cosmic Cliffs. It's a beautiful image of a nebula where lots of stars are being born. And here you can actually see the power of using infrared light. So visible light is actually blocked out by all the cosmic dust that exists in nebula, but infrared light can actually pierce through that cosmic dust. So here you can actually see newborn stars being born inside these clouds of dust. And this is a period of a life of a star that only lasts maybe a few million or tens of millions of years, which is very short in the life of a star, even though it's long for us. So this is the first time we can sort of like look inside these cosmic dusty cave, looking at these newborn stars being born. And up top, you have some older stars. They're still very young, but they're not being born right now in the blue part. And they are pushing out lots and lots of energy. And they're actually carving out these bubbles in the orange dust. So here you can actually see this carving being done in that cosmic dust by the really, really hot young stars inside this Carina Nebula. So a beautiful image. So here you can see the difference looking in the visible light with Hubble, where you don't really see what's going on behind the dust, especially in this blue part here. But with the infrared light with Webb, you can see all this information hidden in the dust. So very powerful. Now, going to the death of a star, you have here what we call a planetary nebula. So when a star that looks a lot like our sun will die, it will eventually sort of puff up and blow out its exterior layers of gas. And what you see here, all these little layers around the bubble in the center, that is the layers of the gas being blown off the dead star at the center. And the dead star that's left over is what we call a white dwarf. It just becomes colder and colder and colder forever. Now, this was taken of the same object, the Southern Ring Nebula, but using two different instruments on the Webb telescope. On the left here, you have the image taken by NIRCam in the near infrared, so it's shorter wavelengths, closer to the color red. And here you have it taken by MIRI in the mid infrared, so it's farther away from the red color with longer wavelengths. And you can actually see they look a little bit different in both cases. So, something very interesting, you might say, this is probably the white dwarf that caused the nebula. But no, actually, there are two stars at the center of this nebula. It's a binary system, two stars that orbit each other. And the one that created the nebula is actually the red one right here. So you can only see it if you look in the mid infrared. So you see the power of looking at different kinds of light, even within just the infrared. And you can see background galaxies throughout the entire image here as well. So this little line that you see right here, that's actually a background galaxy that you're seeing through the layers of gas and dust being blown off the white dwarf. So there's so much information in these images, and we're still digging through them. Lots of stuff to do. Going into galaxies now, this is the colliding galaxies of the Stephan's Quintet. 5 galaxies, 4 of them are interacting together, and you can actually see gas shock waves that are between 2 galaxies that are smashing together. These 2 galaxies are actually almost already merged into one, and these two are smashing together. And in that gas shock wave in the orange, new stars are being born. But if you're looking only in the mid infrared now, using the longer wavelengths, you don't see the stars anymore. All you're left with is the gas skeletons of these galaxies all throughout. And that gas will eventually form stars. So, again, you can see different things depending on the different types of light that you're looking at. And at the center of the very top galaxy, there's actually a huge, supermassive black hole. That's why it looks so bright there, because it's actively eating a bunch of gas and dust. So, lots of hidden information that you can find when you're looking at the mid infrared. And then the last image from the first batch that we released in July is the deep field of galaxies taken by the Webb telescope. All the instruments were used for this. And in this one picture, there are 7,000 galaxies. And this isn't a tiny part of the sky. This is the equivalent of taking a grain of sand, putting it on the tip of your finger, and then extending your arm out. That is the size this image would take on the sky. 7,000 galaxies in there. So many galaxies, lots of different colors. And some of these galaxies are just a few hundreds of millions years old right after the Big Bang. They are like so young. You're looking really far back in the universe. And you can see some of them are kind of warped and deformed. It's kind of weird and interesting. And they're actually deformed because space time, or the fabric of the universe, is being curved by all those galaxies. So they're being sort of stretched out, and this is what happens. You can use those groups of galaxies like big cosmic magnifying glasses. You can see it here. You have one faraway galaxy that's been warped into this sort of half circle because this galaxy here deformed it. So you can sort of get these like weird shapes happening inside there. But what's missing in all of these? What other things could you observe? You could observe so many other things. And you might have noticed there are no solar system objects that were released in July. So since then, we've actually released other objects, other images as well, including this beautiful image of Jupiter. You can see northern and southern lights on the poles of Jupiter. You can see the rings of Jupiter. You can see different moons as well. And something that's amazing about this image, it wasn't created by someone who works on the Webb telescope. It was created by a student, a citizen scientist who's not even in astronomy. She just took the data that we make public for everyone and she created this image herself. So anyone can take the data from this telescope and create their own wonderful images. We've made lots more images since then. This is our cartwheel galaxy. It's a ring galaxy, very rare, that recently interacted with another galaxy, which caused this ring of star formation around it. We just released last week the Tarantula Nebula that's very actively forming a bunch of new stars. You can see all of the detail and the cosmic dust inside, lots of stuff in there. And this is 340 light years across. A huge chunk of that nebula is being captured here. But there's breaking news as well. We're starting to get science coming out. Recently, just a few weeks ago, we released a new result for this planet, Exoplanet WASP 39b. It's 700 light years away. And my colleagues here at the University of Montreal detected the first ever signal for carbon dioxide in a planet outside our solar system. We've never done this before, and we can do this thanks to the power of the Webb telescope. And we know carbon dioxide, or CO2, is an interesting molecule that could indicate if a planet could be habitable. So very, very important and interesting result. But this is only the start. There's so much left to do. This mission will probably last about 20 years. So maybe even some of you will be able to use the telescope and its data. So what will Webb see? We went through some of the examples here, but now you can decide what you think Webb will see because you can participate in our contest. What would you like Webb to see? You can submit your drawings by September 30th and win some really awesome space prizes on this website here. So let me know what you think the Webb telescope can see, because really the sky is the limit, and even beyond that, of course, and it's only the start of this great adventure.
Nathalie, what a fun program. I mean, the images are just breathtaking. They're so scientifically interesting to someone like you who can interpret them and understand them. And thank you so much for taking the opportunity to share with us some of these amazing stories today of what exactly we're looking at. But just on an artistic level, it's the backdrop of our program today is this cosmic cliff. You want to just break out into a tear or song. I don't know, a bit of both. Thank you so much for sharing the art contest as well. I'll make sure all our registered classes have that. And what I want to do now, our classes have been really good in the background about getting ready in the Kahoot. And so if you guys are paying attention, if you were listening to Nathalie well, and you want to have a little bit of fun together, I'll give you guys another few seconds to join in our Kahoot quiz together. Our game pin is 9580506. We've got 33 of you already in. And then after the Kahoot, we'll dive in with an awesome Q&A. While we're waiting for you to pour in, Nathalie, gas skeletons is a phrase I never thought I would hear in any fashion in my life. So thank you for bringing that into my repertoire.
My pleasure.
So for groups that might be new to Kahoot, how you play is we're going to start our quiz in a second. The faster you answer, the more points you get. You don't win anything from this, but you do win our everlasting respect and bragging rights, whatever your name may be. So I'm going to get underway with this, and we will start off and have a little fun. We also have 20 Kahoot quizzes, including one with Nathalie, that permanently live on our Kahoot page. If you want to check them out at the end, I'll make sure you have that in an email. All right. The James Webb Space Telescope mirror is coded in silver, platinum, gold, or bronze. I picked this deliberately obscure image where it looks sort of black and onyx to thwart you. So you don't get any hints at all from the image I've chosen. 8 more seconds. Most of you've got your answers in. Way to go. Who was listening? 4 more seconds. All right, and our answer is gold, which almost all of you nailed. Way to go. This is like, Nathalie, you know this from last year. This is like the best Kahoot group of all time. They're like 90%.
Yeah, definitely.
Cheerful Llama in our lead. Okay, number 2. If you are any of these people, let us know who you are in the chat too. The James Webb Space Telescope looks primarily in what wavelengths? And again, I've given you no hint at all with this deliberately obscure random assortment of colors. Ultraviolet, infrared, visible light, or gamma rays? Is it just looking for hulks out floating in the universe? We don't know. We're going to find it together. Do you want to give us a hint, Nathalie? 1 second.
Oh, it's related to heat.
Infrared. They got it. You didn't need a hint. We didn't need a hint because they nailed it. They're like on the ball. Is Cheerful Llama still in our lead? Power duck. A close second. True or false? The James Webb Space Telescope can see back in time. This is a fundamental part of your talk, like this DeLorean is. Now, what do we think? Kids, I see everyone like yelling out in their classes. This is the power of being a host, is I can watch all the thought processes. 5 more seconds. What's our hint? How do you hit this?
Boy. I don't know.
True. Nailed it. Most of you got this right. So again, as Nathalie said, if you're looking at something that's a billion light years away, you're looking at that not as it is now, but as it was a billion years ago, because it takes that long for the light to get to us, which is really, it's counterintuitive. Nothing in our
it's like magic.
It is like magic. You have such a fun job. Lucky Goat takes our lead with our final question. Okay. Lucky Goat's like going to sweep in here, steal it out from under. How many planets have we discovered outside our solar system? So we've got our 8 planets. Kids have grown up with 8 planets. We grew up with 9. It's very tricky for everyone. But outside of just us, 2, 20, nearly 100, or thousands. It can't be thousands, right? It seems too much. It's crazy.
I didn't actually say this number, so props to the people who get it. Good job.
You know what? This is a great Kahoot crew. Let's see our podium, and then we will dive in with questions. I'm going to head to Miss Flynn's class first as we dive in with Q&A, and our YouTube classes you guys can share in the chat as well. Adorable Duck is second. Epic Falcon is third. Number 1, barely ahead, is Lucky Goat. Way to go. Stole the Kahoot from our Cheerful Llama. Nicely done. Now, thank you guys for participating. Let us know who you are in the chat. We'd love to hear from you. But we're going to head to St. Anthony in Newfoundland, like right near the tip, about as far north as you can go in the province, to head to our grade 6 class for our first question. Hey, guys, welcome in. Hi. Do you have any questions for Nathalie? Hi. right. Any questions? Come on up.
Anybody have a question?
I
think we're a little bit speechless here today, sir.
It's the first day. That's fine. We'll come back in a second. And if you think of any, let us know. But we'll head to Miss Bullock's class, which, by the way, got all three on the podium for the Kahoot.
Wow.
Well, Georgia, welcome in. Unmute your mic. Hi. Way to go on Kahoot, guys. Share a question with us. Hello, hello.
Love the classroom decor.
Yes, it's the best. So what's your question? Come on up.
All right, he's coming.
Yep, take your time. No hurry.
Can we see inside black holes?
Ooh, so that's a great question. And black holes are really tricky to study. So what makes a black hole black? Essentially, a black hole is very, very dense, so dense that the gravity there basically traps everything inside the black hole, which is why if you fall into a black hole, you can't escape. You try to run really, really fast, but you still can't run fast enough. The fastest thing in the universe is light. And even light inside a black hole cannot run fast enough or go fast enough to escape it. So, the way that we try to understand objects is to try to capture light that they emit or shine a light on them and figure out what's going on. But we can't do that with a black hole. We can't see what's going on inside. And even if we were to send a robot or a human or a probe inside a black hole, once it's in a certain region of the black hole called the event horizon, if it tries to communicate back with us using radio signals or something, the signals are also trapped inside the black hole. So right now we have no way to know what's going on inside a black hole. It's totally mysterious. We have theories, but we have no way to prove any of them right now.
Maybe you should draw it in the art contest, what you think is inside the middle of a black hole, hint, hint, nudge, nudge, to win cool space prizes. Great question, guys. Inevitably, we get a black hole question. It's every time. It's inevitable in every space program of all time. Nathalie knows this. She's done like 8,000 million programs. It's an exact figure. Room 3-1, Mr. McIntyre's class joining us in Winnipeg. I know you guys are an audio spot today, so come on in and welcome to the broadcast, guys.
Yeah, go ahead.
Hello.
Hey.
Hello.
What is the exact length of the telescope, and what is your dog's name?
So the exact length of the telescope in meters, I don't actually remember. I just keep saying it's as big as a tennis court at the bottom. And the mirror itself is exactly 6.5 meters wide. But that's already perched up on a standing post. So we sort of say it's like about 2 stories high. The whole thing is about as big as a house. But I forget the exact length in meters because I just keep saying tennis court, tennis court, tennis court in my head. So, but you can look online. It's pretty easy to find.
Yes. And do you want to share your dog's name, or is that like top secret? We don't want to.
Oh, my dog's name. Unfortunately, she's no longer with me. My dog. She passed away a few years ago, but her name was Epsilon, and I loved her very much.
Yes. What a It's very predictable name for someone like you. I appreciate that.
Yeah.
Much. Awesome. All right. Mr. Marker's class joining us up in Sudbury grade 4s. Welcome in, guys. Hey, how you doing? Go ahead.
My name is Harrison, and I want to know how gravity works.
Ooh, no pressure.
Ooh, how does gravity work? All right. So gravity works, we know that it works because it's a fundamental force in the universe. And basically, it works as soon as you have mass. So mass is basically any stuff, any material. And when you have that stuff, it sort of creates a little deformation in the fabric of the universe, in space-time. It's 4-dimensional, it's the 3 dimensions of space and 1 dimension of time. And essentially, when you have mass, it's deforming the space-time, which causes these sort of like little holes in the fabric, not a hole, like a little trough, like a little divot. And things will want to sort of like fall into that little divot in space-time. And it also works in a way that we call radially. So for example, if you have something that's there, that's a mass, gravity will make things attracted to it, but all around it, sort of like in the shape of a sphere all around it. And any point that is the same distance from it on that sphere is affected by the same amount of gravity, which is why if you have enough stuff, enough matter or rock or something like that, it will naturally form into the shape of a sphere or a ball because all the stuff will want to be symmetrical in the shape of a ball because that's how gravity works. It works radially, is how we call it. So, those are some of the ways that gravity works essentially. I'm just using my hands a whole lot here.
That's a fantastic answer. I think for kids too, one thing that I always found fascinating when I was a kid is the idea that I have gravity. Like things are attracted to me, but
Yeah.
I'm just really tiny compared to a planet or a star, so I don't have impact. Think my lamp isn't flying across the room at me, but I am having a gravitational impact on that lamp. I think the coolest way kids can illustrate this in a classroom at home is if you take a sheet, you have like a friend or a sister or a brother.
Like a rubber sheet, yeah.
Flat, and then you put like a ball in it, like a tennis ball. It'll make this sheet sink. So planets and stars do that, but in all dimensions, which is really very cool. Great question, guys. All right, room 212, Miss Hatcher's group will come to you, and then we'll head back to our St. Anthony crew, see if you guys have a question. We're whipping through these questions. But come on in. Hi, room 212. Unmute your mic. Come say hello. More fun that way. Hello.
Okay, go, Trisha.
Hi.
Hi. I wanted to ask what is the meaning of a black hole and what is inside a black hole like?
Yes, we're back to black hole.
It's always a fan favorite. It's a very interesting topic. So a black hole happens when a very, very big star, much bigger than our sun, dies. So the way that stars stay alive, they sort of like want to collapse in on themselves because the gravity of a star is really intense. But at the heart of a star, you have sort of like this reactor. It's fusing a bunch of stuff together. It's making lots and lots of energy. So the star can push on its boundaries. So during the life of a star, the gravity that wants it to sort of collapse on itself and the energy that's pushing out is perfectly in balance. But eventually, a star runs out of fuel, and then all of that matter will sort of collapse in. Gravity wins. And if you have a really big star, gravity really wins, and it all collapses down into a tiny point called a black hole. And black, because again, the gravity makes it such that the light can't escape it. You can't see what's going on. And also, matter can't escape it. If you like toss a ball into a black hole, you'll never see that ball ever again. So, black hole is not really what it is. It's not a hole, but you'll never see it again, essentially. It's sort of as if you put it in a hole. So that's why we don't know what's inside a black hole. We can't just throw something in there and then fish it back out to figure out what happened.
No, I almost like gravity really wins as much as gas skeletons. So thank you again for that.
Okay.
We're gonna head to Miss Flynn's class in just a sec, but I want to note something that's in the background of your shot. So we have this art contest. You guys can submit some awesome art. And almost every space program, I like to highlight something that Nathalie has a really cool poster of behind her, which is something as part of the Visions of the Future Jet Propulsion Laboratory series. So you see these like tuxedo-clad people. They're on a planet. They look really cool. So NASA did this beautiful art series where it highlighted like what it would be like to travel to distant worlds in our solar system and beyond. And I really encourage people to check out that link. It's a really fun thing to get posters too for your class.
And this is my sun shield.
Yeah, it's very cool. By the way, the sun shield, we have an answer for this from YouTube. So 21 meters by 14 meters, or about 35 feet by 45 feet by 30 feet, something like that.
Thereabouts.
Thanks, Sarah. All right, Miss Flynn's group, come on in, unmute your mic, take us away. Hi.
Yeah, my question is, how long does it take to get to space?
Yes.
That's a very interesting question because what is space exactly? Where does the Earth's atmosphere end and space begins? And there's no clear answer. So some people say, okay, when you're about 100 kilometers above the Earth, then you're in space. So there's like different people who put the line differently. It's typically on the order of like 100 to a few hundred kilometers in altitude. So then once you have sort of like a distance, it depends how fast you're going. And typically you have to be going pretty fast to escape the gravity of Earth to try to go up there. So really, you can get into space in the matter of like a few minutes, like 10, 15, 30 minutes, depending on how fast you're going. Then after that, it depends how far out into space you want to go. If you're like, I don't want to just be in orbit around the Earth, I want to like go to the moon. The moon, we're talking about a like 2 days, something like that. We're going back to the moon actually in a few years, and it's going to take astronauts on the order of 3 days about to go to the moon. And then if you want to go further, it took James Webb 30 days to get 1.5 million kilometers from the Earth. So the farther you go, the longer it takes.
But when you go back to the moon, we'll have astronauts. They've got to pack their snacks with them. The telescope could just go up by itself. So there's lots of different things to consider as we go back to space. Room 311, I'm coming to you guys in a quick second. I want to note for all our friends live and on YouTube that we are going to have a Padlet open. Nathalie is the best and has agreed that if you guys have additional questions after the broadcast, you can share them at the Padlet link below. I'll make sure all our registered classes have that. So if you don't get your question answered, please feel free to share there after the broadcast. Now, 311, I'm coming to you guys in just a sec, but I love this question from Markham, Ontario, in Miss McDonald's class. Grade 4s want to know, how do stars make light? And if there were no stars, would the universe be dark?
That's really interesting. All right. So I was talking a little bit about how stars live their lives and how there's like these two combating forces, gravity, and there's this energy, this like reactor. So the way that a star makes light is because it creates energy or heat. So inside of its heart is a nuclear reactor, sort of like what we have, except we take elements and we break them apart into smaller elements. A star does what we call fusion. It takes the smallest elements like hydrogen and helium, it squeezes them together. And when it squeezes or fuses those elements together, that also creates heat and energy. And all of that heat and energy goes throughout the entire body of the star that's made up of lots and lots of gas. It creates almost like a plasma inside of this gas. It's super, super hot. And it's so hot, thousands or tens of thousands, sometimes even hundreds of thousands of degrees hot, the gas starts to glow. So that's how a star becomes bright. All that nuclear fusion heats up the gas and it starts to glow. And yes, if they weren't actually creating that light, the universe would be dark. So there's a part of the history of the universe after the Big Bang, but before the first stars were ever created. And it's called the Dark Ages because there were no stars yet. So it was just totally dark universe at that time.
The more I learn about space from you, the more metal everything seems. Just like that's a thing, and I hope it's like a scientific term. The Dark Ages.
It is called the Dark Ages.
Perfect.
Yeah.
Wonderful. Thank you, astronomers. All right, Mr. McIntyre's class, we got time for 3 more questions. We're going to go to Manitoba, Georgia, and Ontario in that order. Come on back in, turn on your mic, room 311, and take us away if you have a second question. Hey, guys.
How can the James Webb Telescope see the past?
Yes.
Yeah. So I can go a little bit more into detail. So we know that it takes time for light to go from point A to point B. So for example, we are in the solar system. The sun is relatively close to us, but it's still pretty far. It's like, tens and hundreds of millions of kilometers away. So light goes really fast, but it does take some time to get from point A to point B. It's not instant. So for the sun, it takes about 8 minutes for the light to get from the sun to the Earth. So that means right now, the picture that we see of the sun, the photons or the light that we're looking at is 8 minutes old. We're not seeing the sun as it is right now because we can't see it live. We have an 8-minute delay between us and the sun. So if the sun were to like disappear like that all of a sudden, we wouldn't know for 8 minutes. Shouldn't happen. That shouldn't be a problem or anything like that. But the sun is just next to us. It's like no problem. The stars and the galaxies we're looking at are much, much farther away. So far away that we use a light year, which is the distance light. Again, the fastest thing in the universe travels in 1 year. We use that as a measuring unit for distance, which makes it really easy because then you can say, well, that galaxy is 1 billion light years away. That means the light that I'm looking at is 1 billion years old. There's a 1 billion year delay between what the galaxy is doing now and what I can see. So we're sort of looking at the past because we're looking at older light that these very distant objects emitted a long time ago. So we don't have an actual idea of everything that's going on in the universe right now because of this delay going on because of the light.
Very, very cool. That was a great explanation. Miss Bullock's class, head to you guys and Mr. Margaret to wrap up. Come on back into Georgia, folks. Hi.
Are there any other living things on any other planet? And how long until our sun dies out?
So yeah, the search for alien life is a really big question we're trying to answer right now. And we're searching for alien life on planets in the solar system, but also outside of the solar system on exoplanets, like I mentioned. Currently, we have not found any clear evidence of alien life, but we have lots of interesting candidates, worlds that might look like the Earth outside the solar system, or even Mars or some moons that orbit Jupiter or Saturn, or even maybe in the atmosphere of Venus, there might be life. So we're trying to answer this question right now. And I think in the next 10 to 20 years, we might see the first signs of alien life. And for the lifetime of our sun, we still have about 4 to 5 billion years before the sun dies. So we got plenty of time.
Yes, it's not going to wink out. We're not going to have it
No.
disappear anytime in the next 8 minutes or anytime after that either. All right, Mr. Margaret's class, to wrap up, I will note really quick for everyone who might need to go, again, our art contest is here. One of the things you can win is, again, these 8x10 prints of the cosmic cliffs, other cool things that the James Webb Space Telescope has seen, and some awesome books. So please do submit today. All the instructions are on that website below. If you've got additional questions for Nathalie, padlet.com/our-JWST. And if you want to check out all the cool stuff that the Webb Telescope is checking out, web.nasa.gov, a beautiful website to keep the excitement going. But let's head to Mr. Margaret for our final question. Hey, guys.
Hi, my name's Tova, and I was wondering if you think that we'll find any new forms of life.
So yeah, I think that maybe not with the Webb telescope, but with the Webb telescope, we'll be able to find planets that might be very interesting to study further on with other kinds of telescope to find life. So we mentioned it a little bit in the Kahoot. We've discovered over 5,000 exoplanets, and in our galaxy alone, we think there are hundreds of billions of exoplanets. So I think that somewhere out there, even a very simple form of life exists, but can we find it? That's the hard thing. So that's where scientists have to work really, really hard, and it's going to continue being a big scientific mission. And I hope some of you will be able to help out going into science later on to answer that question.
I love that you always answer the question this way, and I will note for our classes, of all the astronomers, astronauts, amazing people involved with space that we have on, virtually all of them highlight the fact that there's just so much space, there's so much out there, that it would be so unlikely for there to be no other planet in the whole universe that life developed on. It happened so quickly here on Earth, and so fast it diversified, and we ended up with tons and tons of different living things that you'd think that somewhere the conditions would be just right. That's why we look for things like carbon dioxide, like water on other planets. So here's hoping that in your lifetime you get the chance to find something like that, because it would be the most special thing ever. Dr. Ouellette, thank you so much for joining us today. It was so nice having you. We have classes from all over Canada and the US, and as you know, what we do to end every broadcast is bring them in to say a big thank you and farewell. So Miss Flynn's class, Mr. McIntyre, Miss Bullock, Mr. Margaret, if you could join me in saying a big goodbye. You are all in the broadcast. Thank you so much, everybody. Thanks.
Bye.